Energy flows and efficiency in the home. Consider the home a thermodynamic system that experiences several energy flows. The efficiency of keeping or removing energy from the house depends on how well the home is insulated from losing energy or gaining energy from the outside environment. It's also affected by the flows caused by the devices, appliances, and people inside it. The effects of how well the home is able to maintain or lose heat is critical to saving money and energy and determines the residence's environmental impact. This all motivates a quantitative understanding of how technology can impact the energy flows and efficiency in the home.
In order to do this, we must first model the energy flows of the house. We shall do this for a heated, occupied system enclosure, or colloquially, a house. The house is shown here schematically, with windows making up one side, with one floor of approximately 200 square meters of area, and a roof at 3.1 meters off the ground, which is slanted at angle theta relative to the plane of the house. The balance equations which describe this system are given here. We neglect the entropy balance because it is not relevant. We take mass to be steady state, but energy not necessarily. We applied the following simplifications, beginning with the fact that the house shall remain stationary and is constructed with rigid walls, which is to say that we have negligible movement or work compressive terms. We will pick the temperature internally to be uniform, which is to say that any energy flows that are noticed shall be felt instantaneously and evenly. We neglect the mechanical energy contributions, and we also consider the heat capacities to be ideal. Lastly, we take the building materials to have low albedo or low reflectivity of incoming radiation. Applying these, we get this, crossing things out, we get this balance, and combining this with the understandings that we get from the expansion of internal energy, we obtain the following balance expanded with these terms describing the house. These terms are 6 in number, with 4 relating to building parameters and 2 relating to energy transport systems, which is to say heating and cooling. With the geometric parameters included, the numbers look like this, and in hot weather operation from consumer and government data, the energy looks like this. In cold weather operation, we have a much reduced solar term, and the Q from the walls increases in its relevance. We also are neglecting the air conditioning required to cool during the winter, as we are neglecting the heating required during the summer. These building parameters and transport systems are what may be changed to increase the efficiency of the host, especially, for our purposes, the building parameters.
Energy efficiency in buildings is significantly improved by insulation. Insulation reduces heat conduction and increases reflection of thermal radiation from the sun.
Insulation is important because the majority of people do not have an insulated home or a properly insulated home. This is mostly due to the cost of insulation, as well as problems with awareness, cost, and the insulation materials themselves. The issues that can cause energy loss are examples such as the mold and mildew damaging the insulation, or a poor air seal around the windows and doors, issues with how the house was built, as well as non-insulated areas such as the attic, basement, garage walls, and the floors above the garage.
The R value, as seen in earlier equations, is a measure of how well the material resists the flow of heat, with units varying by system. As the value is dependent on thickness, compressing the material will decrease its effective R value. While it might seem tempting to aim for the highest R values possible, the reality is that there are diminishing returns for the cost of increasing R values. At higher values, a 1% improvement in energy efficiency can nearly double the cost. All of this together impacts the heat flows of the energy balance. A poorly insulated house will have large and negative flows out during the winter and large and positive flows in during the summer. This varies based on temperatures between the environment and the home. The goal is to limit the heat flows at any time to 0 as we approach perfect insulation. As heating technology becomes more efficient, a given amount of energy input can produce a given temperature change sooner, using less energy over time. Increasing the albedo from 0.2 to 0.65 and the R value from 8 to 32 decreases the energy values by around 30%. As you approach perfect insulation, this means hundreds to thousands saved yearly on energy costs. The impact on the environment, if we consider all homes in the country, would be largely beneficial too.